Hello again, this is the second lecture of the fourth week. What I wanted to do today was to continue with graph-based coverage criteria. We saw how to test code based on the graph coverage criteria. The basic idea was to take the control flow graph, model it as a graph, and then consider the various structural coverage criteria to be able to do graph coverage. And then we augmented the CFG with definitions and uses, looked at DU pairs, DU paths, and tested it for data flow criteria. And what did we achieve by doing this? It was basically white box testing of code. We could cover the code, see what statements were executed, how many times loops were executed, where loops skipped, and so on. And through examples, we saw that it was indeed useful to find errors in codes. Now I want to continue to use graph coverage criteria, but instead of considering code, I want to be able to work with design, graphs for design models. Right? When it comes to design, the phase of testing that we are looking at is what is called integration testing. And integration testing basically assumes that a design puts the software into various modules. It puts together these modules and tests them. So what I want to spend some time on with this lecture is to help you understand the traditional or the classical view of integration testing. What is integration testing? How has it been defined in the popular textbooks available on software testing? How do graphs corresponding to integration testing look like? Right? So today we will look at the classical view of integration testing. Any old book on software testing that's existed for many decades will use this view of integration testing. In the next lecture, what I'll tell you is graph models for design and how to apply structural and data flow coverage criteria on those graph models. We have to define slightly new structural and data flow coverage criteria to be able to cater to graph models for design. We'll do that in the next lecture. This lecture will just spend on understanding integration testing as it's always been classically presented in several textbooks in software testing. So when I say software design, what is it? Software design for a large piece of software is basically tells you details about how this large piece of software is split into modules. Let's say a software runs into several thousands of lines of code or even millions of lines of code. It's all not going to be one flat piece of code, right? It's going to be split into several components. Each component is going to be designed and implemented by separate teams, separate individuals, and then they're all going to be put together modular way to be able to constitute the whole piece of software. Typically for software, popular design languages are UML, Unified Modeling Language, SysML, System Modeling Language, and some proprietary embedded software are modeled using proprietary design languages or even languages like Simulink, Stateflow, etc. In this lecture, we really won't consider each language for design and look at models for these languages. Instead, I'll assume that design is just a way that tells you how a software is split across modules. And then we will see how these modules are put together and tested. So what is a module? A module or a component, these terms will be used interchangeably, is a self-contained element of a piece of a software or a system. What do I mean by self-contained? By self-contained, I mean that it takes inputs, executes and produces outputs. For its execution, it's not dependent on another piece of software running or calling another piece of software or availability of data from another piece of software. Right? So it executes as a standalone entity, stops its execution, produces outputs and stops. Simplest view of a module would be a procedure in C or a method in Java. Right? Individual method. Modules interact with each other using what are called interfaces. We'll see what are the various kinds of interfaces, but interfaces always have to be well defined. What is an interface? An interface, you can think of it as implementing a mechanism for passing control and data between modules. So one module can call another module, a procedure or a function can call another procedure or function, in which case it passes control to the other called procedure or function. And when it calls, it can call it with certain data, right? It says, please return this data to me, run it with this input and return the following input. So it also exchanges data between the called procedure and the callee procedure. right? So interfaces are basically mechanisms that facilitate this call and return, control of call and return of data. Integration testing is basically a phase of testing that deals and tests if all the modules have been put together properly as per design, and whether all the modules put together meet the functionality that they're supposed to meet together. When is integration testing typically done? If you remember the phases of testing and the levels of testing that we saw right in the first week, integration testing immediately follows unit testing. Right? When I mean integration testing here, I mean integration testing of software modules. There is also what is called software hardware integration testing, which involves putting the piece of software in the hardware and then testing. That's not the focus for today's module. We mean software integration, putting together individual code components and testing the software, right? Modules can be put together in several different ways, but however they are put together, the way of putting them together is predetermined and it's incremental. It's not like, suppose I have 15 modules, we develop all the 15 modules and one fine day just sit and put together, right? We don't do that. We have a well-defined incremental way of putting together all the modules. Integration testing, basically what it does is that it tests if the modules that have been put together are working fine. While testing for this, it focuses on testing the interfaces. How are the calls and returns happening? The focus is on that, designing test cases to see if there are any kind of errors on these interfaces. So we'll spend some time understanding what are the various types of interfaces and how we will be dealing with them. The most common interface is what is called procedure call interface. So here we assume that a software procedure, a function or a method in one module calls another procedure or a method in another module, right? This call could be called parameter passing, call by value, right? Several different ways that you would study in any standard C programming would apply to this kind of interfaces. Both control and data can be passed in both the directions. So when it calls another module, it transfers control to the other module, and while it transfers control, it also passes some data. And when the call module returns back the control to the main module, while returning back, it could pass some data. Second popular type of interface is what is called a shared memory interface. Here we assume that there is a block of memory that is available at some place. This block of memory could be within one of the modules that are sharing the interface, or could be available or created by a third module in a different interface. How do these two modules communicate? They communicate by reading from that block of memory and writing onto that block of memory. So there's a common shared global location, and these modules communicate by reading from and writing to that value. Typically several systems software like operating systems, embedded software, they all use these shared memory interfaces. The third popular interface is what is called a message passing interface. Here what we do is that we assume that there are dedicated channels or buffers available, and various components communicate by sending and receiving messages on these channels. Popular examples of systems that communicate with message passing interface are what are called client server systems, right? IoT is a very popular system these days that basically says that each individual IoT device is a client, and then there are aggregator nodes, common nodes. So it can be thought of as a kind of a client server system. Web apps, web applications that we all popularly use, right? Social networking applications like Facebook, Twitter and all other things, they also exchange a lot by using message passing interfaces. So this gives you a broad idea of what the various interfaces could be, but the testing methodologies that we would see today are independent of these kind of interfaces. This is just to educate you a bit about various interfaces that could actually exist. When we look at testing techniques for integration testing, for today's lecture, we'll abstract out and not worry about which is the kind of interface that is in play. And why is it important to test for interfaces? It's important to test for interfaces because a lot of errors could come from interfaces. In fact, empirical studies in software engineering, empirical studies are studies based on collecting factual data, right, from various organizations which contribute to these data. They use a lot of statistical tools to be able to come to conclusions. Such empirical studies actually indicate that almost 25%, at most 25% of the total errors that come in software are basically related to interface errors, wrong calls, wrong returns, whatever they are. What could be these kinds of errors? So here is a broad category of the various kinds of interface errors that can happen. It could be, error could be related to module functionality, in the sense that let's say one module is calling another module. It could assume that the module that it's calling offers some kind of functionality for sure. But then it might be the case that the module that is being called has inadequate functionality, is not being able to offer the kind of functionality that it's assumed to offer. There could be errors because of that, and there could be errors in where the module that is being called is located, right? It could be in a wrong place, it could be in a place where it's not being able to call it easily, right? Or the module that it's calling could have been removed, could have been changed, a lot of things could have happened. The next kind of error is the actual interface error itself, in the sense that the interface can be misused. Suppose a procedure is calling another procedure, let's say the first one, procedure call interface. It could be the case that you're passing a wrong parameter type, you're passing parameters in the wrong order, you've missed passing certain parameters, you're trying to pass more parameters. Any kinds of errors could happen, right? The next is what is called inadequate error processing. So here what we assume is that, let's say suppose two modules are there. One module is calling another module. You are also supposed to do some elementary debugging or error processing as a developer. Let's say the module is error prone. The callee module is supposed to have a handler that's supposed to handle an erroneous message from the module that is returning the value. Maybe that was not correctly done, right? Or it was assumed that certain kinds of errors would be there and those kinds of errors were not possible. So there could be interface errors due to incorrect error handling. The next is initialization and other value errors. You could pass wrong initial values, you could pass wrong data values, you could have missed initializing values, anything can happen. The last kind of popular interface errors are related to timing and performance. Sometimes you not only call a module, you want the call module to respond to you fast enough. You wait for some time, and if there is no response, you time out, right? And there could be errors because you decided to time out early or you waited for too long. There could be errors related to these. But the basic summary is that interfaces are important. They can cause up to 25% of the errors that occur in typical software. So it's important to be able to test interfaces. And integration testing focuses only on that, right? Before we move on and look at various approaches or methods of doing integration testing, it's useful to understand two other terminologies related to testing. As I told you, right, integration testing puts together the modules and tests them as and when they are ready. The typical belief is that integration testing need not wait until all the modules are ready, because that will be too late, right? Suppose you had the typical large systems may have hundreds of modules. It doesn't make sense to wait till all the modules are ready. So you test the system as and when the modules become available, right? So when we are testing the system as and when the modules become available, you may not have the full test system that is test ready. So what you have to do is a process in testing that is referred to as scaffolding. So what happens in typical scaffolding is that whichever portion of the software is missing or is incomplete, you try to substitute for it, right? There are two kinds of popular scaffolding that is available. One is what is called test stub and the other is what is called a test driver. What is a test stub? The word stub says that suppose you had a module which you wanted a module and you didn't really have it. So you create a dummy module which behaves as if the module that you wanted was there, right? So it takes some values, it returns maybe some dummy values, but it doesn't represent the module. It is just a dummy entity that is being substituted for the actual module. right? This dummy entity need not represent the actual module. It can differ a lot from the actual module. That's all right, but we still need a dummy entity to be able to go ahead and test. So when I substitute an actual module with a dummy entity that behaves like the actual module in terms of interacting with the interfaces, I have developed what is called a test stub. The next kind of scaffolding is what is called a test driver. What is a test driver? That is a software component that replaces a component that is supposed to take control of the calling of the software component. Right? Suppose you have 3 modules that have to be tested for integration testing. You want to put together and test. It so happens that the 3 modules are being called by the parent module, let's say one after the other. But the parent module itself may not be ready. So then what you do is that you create a dummy parent module. It's called a test driver, and make this dummy parent module just call these 3 modules, right? So when you do that, then that kind of scaffolding that you develop is what is called a test driver. They are very, very needed for integration testing. Integration testing cannot happen without stubs and drivers. So just to succinctly repeat what I said till now, what is a stub? A stub can be thought of as a module that is like a dummy that represents the actual module. What is a test driver? A test driver is a dummy, but not for replacement of any module. It's a dummy module that calls the other modules that are in the lower level than this. So there are 5 broad approaches to classical integration testing. Most of the books in software testing would refer to these approaches, the older books. The 5 broad approaches are incremental testing, top-down integration testing, bottom-up integration testing, sandwich testing, and big bang testing. So we look at them one after the other. What is incremental testing approach to integration testing? So as the word says, incremental means you do it in an incremental fashion. As and when you move, you keep integrating and testing, right? So the complete system is built incrementally, phase by phase or cycle by cycle. As and when the modules of one cycle are ready, I put them together, do integration testing. The next cycle is ready, I put them together, do integration testing. And each cycle is tested for modules working in that cycle together. Errors are fixed then and there, and what is done later on is incremental testing. The cycle that has been put together first is not retested all over again. Another popular approach to integration testing is what is called top-down integration testing. So here it assumes that the system design that breaks up a software into its various modules is hierarchical. So it assumes that modules are organized in a hierarchy of levels. So here is a small example. If you refer to this figure here, there are 7 modules in this figure: A, B, C, D, E, F, G. And as you see, the modules are arranged as if they were the vertices of a tree, right? These vertices of a tree represent implicit hierarchy that is available in the module. So here what it means is that there are 3 levels of hierarchy. Modules E, F and G are at the lowest level of the hierarchy. C calls these modules E, F and G. Modules B, C and D are at the next high level of hierarchy. And module A is at the topmost level of the hierarchy, and that calls all the 3 modules B, C and D. It so happens that in this case the figure looks fairly balanced and complete. At every level there are equal number of modules, but it need not be like that. What I meant is that there are several modules organized into levels. At each level, the modules from the previous level call the modules in this level, right? So it has a tree or a directed acyclic graph structure to it, right? So the terminal modules are the modules that occur in the leaves of a graph. In this case, B, E, F, G and D are the terminal modules. A is a top level module. C is an intermediate module, right? This is my reference document to begin the next phase, which is top-down integration testing and bottom-up integration testing for that matter. So I have such a structure. What do I do when I do top-down integration testing? So there is a top, and I start from the top, which is the module A, and I go down as I do integration testing. So that's what is top-down integration testing. So what I do, I'll explain it in these figures. So this is the total software design. There are 3 levels, 7 modules. I want to put them together one after the other and test. And I want to put them together and test in a top-down way. How do I go about doing it? Initially, I start with the topmost module, which is the module A. Module A calls modules B, C and D. Right? It's not wise to put all B, C and D together and test A. I would want to test how A works with B, how A works with C and how A works with D independent of each other. And I want to test how A works with B, C and D together. So what I do first is that I'll keep A. A is unit tested ready. I keep B, which is a unit tested ready actual module. What I do is I create stubs for C and D. I create test stubs for C and D. So even if actual modules C and D are ready, I don't put them to now. I just make them as stubs, dummies. And why? Because my focus is to test the interface between A and B alone. I test this part. And now what I do, assuming that I've tested all bugs if found fixed, now I move on to testing the next interface. I could test the interface between A and C or A and D. In this particular example, I'm testing the interface between A and D. Order doesn't matter. You could do A and C before you do A and D. There's no problem. So if I test the interface between A and D, it's not wise to stub B now, because B is tested, integrated with A, so I retain it as it is. I remove the stub for D. I replace D with the actual module, right? And then I test whether the interface between A and D as added to the interface between A and B, which was already tested, works fine. In the third step, what I do is I replace C with the actual module. Right? Now remember, in our graph in this figure, C is a module that in turn calls E, F and G. Right? So when I replace C with an actual module, it comes with its calls for E, F and G. But for now, I still want to focus and test if the interface between A and C is working fine. So I don't keep the modules C, E, F and G actual. I stub them out, or they may not be ready. I don't really worry about it. I just stub it out now. Now at this phase, what am I testing? I am testing the interface between A and C to be working fine after having tested the interface between A and B and A and D. Right? I still have to go on because I have to remove these 3 stubs and carry on. Right? So I can remove them in any order. Here I have removed the stub for E, replaced it with the actual module for E. Now I am testing this interface between C and E. And I move on. I remove the stub for F, replace it with the actual module for F, test the interface between C and F. And the last step, I remove the stub for G, replace it with the actual module G, and interface test the whole system. So this is what is called a top-down approach to integration testing. I begin with the topmost module A, then I go and test the second level modules B, C and D. I can test them in any order, but typically I would want to do B and D because testing C will involve moving to the third level. Between B and D I can test them in any order, and then I move on to the next level, which is testing C, and here there are 3 more modules to be tested, and because there is no further calls, I can test them in any order. So I go from top all the way down and integrate the modules one after the other and test them. So this is how top-down integration works. The next approach to integration is what is called bottom-up integration. So here, as the name says, I start from the modules at the lowest level and keep moving up in the hierarchy till I reach the topmost level, right? What is the lowest level module? It is a module that looks like this. E, F, G, B, D are lowest level modules. They don't invoke any other modules, right? Now, to be able to put together the lowest level modules, if you go back and see this figure, E, F and G are the lowest level modules, right? Suppose I want to be able to test the interfaces for E, F and G. How do I test them? E, F and G don't really call each other as per this figure, right? Who calls E, F and G? It is actually C that calls E, F and G, right? But my goal is to go bottom up. If I just test directly C, E, F, G, I am violating the approach of bottom up integration testing. I test the bottommost level with one level top, which is C. I don't want to do that. So what I now do is I create a dummy for C, right? What is a dummy for C? I need a dummy that behaves like C in terms of calling modules E, F and G. Such a dummy is what is called a test driver, right? So I create a test driver module that invokes the lowest level modules to be integrated. I test for that level, lowest and one level up. And then this test driver module is actually replaced with the full module, and then I go one level high and introduce the next test driver, right? So that's what is illustrated in this figure. My goal is to do bottom up. I start from the lowest level module. So I start from E, F and G. I don't want to put C as it is, so I write a test driver for C that calls modules E, F and G. And the next step, I replace C, the test driver, with actual full module C. Now my idea is to integrate test B, C and D. I still don't want to include A because A comes at a next level above in the hierarchy. So I now write a test driver for A and then test the integration of modules B, C and D at the second level. Finally, I replace the test driver for A with the actual module and test the whole system, right? So this is how top down and bottom up testing works. For top down, to recap, I need stubs to test one interface at a time. Stubs are dummy modules that replace other modules, just return some dummy values or fixed values that are consistent with the module values that it would return. And I do top down, start from the topmost module and keep going down my hierarchy. In bottom up, I start from the lowest level modules and keep going up in the hierarchy. But to integrate test the lowest level modules, I need to be able to write test drivers, which are dummies, which will, for the namesake, call the modules at each level that have to be integration tested, right? These two are the most popular integration testing techniques. There are other popular techniques called sandwich and big bang. So what does sandwich do? As the name suggests, it's somewhere between top down and bottom up. Sometimes it uses top down, sometimes it uses bottom up, sometimes it uses a mix of them, right? It could be the case that the lower level modules are tested using bottom up, the higher level modules are tested using top down, and then they are put together in a sandwiched way. The next popular approach to integration testing is what is called big bang testing. All individually tested modules are put together in one shot and tested. I'm personally not a very big fan of big bang testing because I feel that it's very difficult to isolate a fault when an error happens in a fairly large piece of software. I would advocate that when there is a clear-cut notion of hierarchy, you follow either top-down or bottom-up based on which are the modules that are readily available for you to integrate and test. Yeah, so now what we will do in the next lecture is we'll go back to our favorite graph models. Our focus is now to look at graph models for design and see how they apply to integration testing as we learned today. So what do graph models for integration testing look like? If you see the ones that we saw here, right? These are graphs. All these are also graphs. So what do the nodes in these graphs represent? They represent modules. Sometimes they could represent stubs or drivers, right? What do the edges represent? They represent interfaces. As I told you, I really don't worry about which is the correct interface for now. When we go later weeks, look at object-oriented software, web software, at that time we'll worry about interfaces. But for now, I consider them as just edges. Now we want to see how to apply structural coverage criteria, which will deal with calls on the interfaces, and how to apply data flow coverage criteria, which will deal with parameter passing and return. So in the next module, we'll look at graph models for integration testing and specifically consider coverage criteria for all these things. Thank you.